What specific problem does your method aim to solve in the context of information retrieval using neural embedding models?
Our method aims to address the fundamental limitations of neural embedding models in information retrieval, specifically their inability to represent all combinations of relevant documents for complex queries. We establish a theoretical basis by connecting geometric algebra and communication complexity theory, demonstrating that there exists a lower bound on the embedding dimension required to accurately capture the relationships defined by a given relevance matrix. Through empirical analysis, we show that as the number of documents increases, there comes a critical point where the embedding dimension is insufficient to encode all relevant combinations, leading to retrieval failures. Additionally, we introduce a simple dataset called limit to illustrate these limitations, revealing that even state-of-the-art models struggle to achieve satisfactory performance on this task. Ultimately, our work highlights the need for alternative retrieval approaches, such as cross-encoders or multi-vector models, to effectively handle the increasing complexity of instruction-based queries.
How does the proposed method or algorithm work? Illustrate it step by step, including the theoretical basis and the empirical approach you utilized.
The proposed method connects theoretical insights from communication complexity theory to the practical limitations of embedding models in information retrieval. First, we establish a theoretical framework by proving that the embedding dimension required to represent a given set of relevant documents and queries is bounded by the sign rank of the relevance matrix. This theoretical basis indicates that for any fixed embedding dimension, D, there exist combinations of documents that cannot be represented, highlighting a fundamental limit of embedding models. Next, we empirically validate this theory through a free embedding optimization approach, where we directly optimize the vectors for queries and documents against a target relevance matrix using gradient descent. This allows us to identify a critical point, termed the critical endpoint, where the model's ability to achieve 100% accuracy breaks down as the number of documents increases. We gather data from these experiments and fit a polynomial regression to model the relationship between embedding dimensions and the number of documents that can be effectively represented. Finally, we create a simple dataset called limit to demonstrate these limitations in a real-world context, where even state-of-the-art models struggle to achieve satisfactory performance, thus empirically confirming the theoretical bounds established earlier.
Can you come up with a simple yet illustrative example to demonstrate the workflow of your proposed algorithm? Walk through the steps while explaining the role of each component.
To illustrate the workflow of our proposed algorithm, consider a simple dataset where we have 3 documents: John likes apples, Mary likes apples, and John likes bananas. The goal is to retrieve relevant documents based on the query, Who likes apples? 1. Document and query representation. Each document and query is represented as a vector in a high-dimensional space. For instance, John likes apples might be represented as a vector, v_1, Mary likes apples as v_2, and the query Who likes apples as u. 2. Relevance matrix construction. We create a binary relevance matrix A, where A_ij equals 1 if document j is relevant to query I. In our case, A would indicate that both v_1 and v_2 are relevant to the query U. 3. Score matrix calculation. The algorithm computes a score matrix B using the dot product of the query and document vectors, B equals U_TV, where U contains the query vectors and V contains the document vectors. This step quantifies how well each document matches the query. 4. Ranking and retrieval. The algorithm ranks the documents based on their scores in B and retrieves the top K documents. For our example, if v_1 and v_2 score higher than other documents, they will be returned as relevant to the query. 5. Empirical testing. Finally, we empirically test the algorithm's performance using the limit dataset, which challenges the model with various combinations of queries and documents. This step validates the theoretical limits established in our work, demonstrating how the embedding dimension impacts retrieval success. This workflow highlights the critical components of our algorithm, from vector representation to empirical validation, showcasing the theoretical underpinnings and practical implications of embedding models in information retrieval.
What are the main theoretical and practical benefits of using your method compared to existing alternatives in neural information retrieval?
The main theoretical benefit of our method lies in establishing a lower bound on the embedding dimension required to represent combinations of relevant documents and queries, which is grounded in communication complexity theory. This theoretical framework reveals fundamental limitations of embedding models, showing that for any fixed dimension, there exist binary relevance matrices that cannot be captured, thus highlighting the constraints of current neural retrieval approaches. Practically, our empirical analysis demonstrates that even state-of-the-art embedding models struggle with simple tasks when faced with a high number of combinations, as evidenced by our limit dataset, where models achieved less than 20% recall. In contrast, alternative architectures like cross-encoders and multi-vector models show significantly better performance on the same tasks, indicating that they can handle the complexity of retrieval more effectively. Overall, our work not only provides a theoretical basis for understanding these limitations, but also emphasizes the need for more expressive retrieval architectures to address the challenges posed by complex queries and relevance definitions.
How is the effectiveness of your method validated through experiments, and what metrics or benchmarks did you employ to demonstrate its performance?
The effectiveness of our method is validated through a series of experiments that utilize a dataset we created called Limit, which is designed to test the limitations of embedding models in retrieving top-K relevant documents. We conducted free embedding optimization experiments, where the vectors for queries and documents were directly optimized using gradient descent, allowing us to determine the critical endpoint at which models could no longer achieve 100% accuracy. The results were modeled with a polynomial regression, revealing that even the largest embedding dimensions, up to 4096, could not adequately represent all combinations of documents for web-scale search tasks. Additionally, we evaluated state-of-the-art embedding models, such as GRIT-LM and E5 Mistral, on the limit dataset, finding that they struggled significantly, achieving less than 20% recall at 100 in the full setting. This empirical evidence, combined with theoretical insights regarding the sign rank of the relevance matrix, demonstrates the fundamental limitations of current embedding models in handling complex retrieval tasks.
What specific results did your experiments yield, particularly concerning the limitations of embedding dimensions in capturing complex query relevance combinations?
Our experiments revealed that embedding models struggle significantly with complex query relevance combinations, particularly as the number of documents increases. We identified critical endpoints for various embedding dimensions, showing that even the largest dimensions, up to 4096, could not capture all combinations of top-K relevant documents, with critical N values reaching up to 250 million for the highest dimensions. In our limit dataset, state-of-the-art models achieved less than 20% recall at 100, indicating their inability to solve even trivially simple tasks when faced with dense combinations. Furthermore, we found that models trained with diverse instructions performed better, suggesting that training diversity allows for more effective use of embedding dimensions. Overall, our results underscore that the dimensionality of embedding models imposes fundamental limits on their capacity to represent complex retrieval tasks, necessitating alternative architectures for effective retrieval.